Hello everyone, welcome to the lecture today. We're going to talk about birds. The success of avian theropods, a class of bipedal vertebrate chordates with feathers, wings, and a beak, lies in the development of said feathers. Developed from reptilian scales, feathers are the ideal adaptation for flight, serving as lightweight aerofoils that are easily replaced if damaged. Today, birds are the most diverse of all terrestrial vertebrates, with 28 orders containing a total of 166 families and about 8,600 species. The taxonomic group reptiles used in evolutionary systematics is paraphyletic because it excludes birds and mammals, which share the common ancestor as the reptiles. In cladistics, such groups are regarded as invalid when constructing classification schemes, since cladistics allow only monophyletic groups, or clades, as a basis for taxonomic groupings. However, in evolutionary systematics, paraphyletic groups or evolutionary grades are sometimes permitted in order to reflect biological similarities. The birds evolved from reptilian ancestors, the Saurischian dinosaurs, probably in the Jurassic period, and modern birds still have scaly legs like reptiles. Birds are endothermic. The skin is dry and loose and has no sweat glands, so cooling is effected by panting. Their efficient lungs and four-chambered heart ensures a good supply of oxygen to the tissues. Birds can therefore sustain a high body temperature and level of activity necessary for flight. Modern birds lack teeth and have only vestigial tails, but they still retain many reptilian characteristics. For instance, birds lay amniotic eggs. Also, reptilian scales are present on the feet and lower legs of birds. Two primary characteristics distinguish birds from living reptiles. First, feathers are modified reptilian scales made of keratin, just like hair and scales. Feathers serve two functions, providing lift for flight and conserving heat. The structure of feathers combines maximum flexibility and strength with minimum weight. Feathers develop from tiny pits in the skin called follicles. In a typical flight feather, a shaft emerges from the follicle and pairs of veins develop from its opposite sides. At maturity, each vein has many branches called barbs. The barbs, in turn, have many projections called bobules that are equipped with microscopic hooks. These hooks link the barbs to one another, giving the feather a continuous surface and a sturdy but flexible shape. Like scales, feathers can be replaced. Among living animals, feathers are unique to avian theropods. The presence of feathers in non-avian theropods is evidenced in the fossil record. Second, the bones of birds are thin and hollow. Many of the bones are fused, making the bird skeleton more rigid than a reptilian skeleton. The fused sections of backbone and of the shoulder and hip girdles form a sturdy frame that anchors muscles during flight. The power for active flight comes from large breast muscles that can make up 30% of a bird's total body weight. They stretch down from the wing and attach to the sternum, which is greatly enlarged and bears a prominent keel for muscle attachment. Breast muscles also attach to the fused clavicles that form the focula No other living vertebrates have a focula or a keeled sternum. Birds are dinosaurs because they share the derived characters of the Dinosauria, diagnostic characters that might be easily observed in the fossil records are used to deduce to whom birds are related. Diagnostic features of living birds include loss of teeth, high encephalization quotient, pygostar, Carpometacarpus, bipedal, Tassometactarsus, digit 1 in back, digits 2, 3, and 4 in front, pneumatic bones, focula, carinate sternum, synsacrum. Modern birds share many highly derived anatomical features with many Maniraptoran theropods. This lecture demonstrates that many supposedly uniquely avian features are distributed throughout the theropoda. However, differences between avian and non-avian theropods include the presence of all vertebrae in Maniraptoran theropods, an unfused pelvis, and an unfused foot. A 150 million year old fossil, Archaeopteryx, was found in 1862 in a limestone quarry in Bavaria. The impression of its feathers stamped clearly into the rocks. The skeleton of Archaeopteryx shares many features with small theropod dinosaurs. About the size of a crow, Archaeopteryx had a skull with teeth, and very few of its bones were fused to one another. Its bones are thought to have been solid, not hollow like a bird's. Also, it had a long reptilian tail and no enlarged breastbone such as modern birds use to anchor flight muscles. Finally, the skeletal structure of the forelimbs was nearly identical to those of theropods. Because of its many dinosaur features, several Archaeopteryx fossils in which the feathers had not been preserved were originally misclassified as Compsognathus, a small theropod dinosaur of similar size. The remarkable similarity of Archaeopteryx to Compsognathus has led paleontologists to conclude that Archaeopteryx is the direct descendant of dinosaurs. Indeed, that today's birds are feathered dinosaurs. The recent discovery of fossils of feathered dinosaur in China lends strong support to this inference. Caudipteryx, for example, is clearly intermediate between Archaeopteryx and dinosaurs, having large feathers on its tail and arms, but also many features of dinosaurs like Velociraptor, because the arms of Caudipteryx were too short to use as wings. Feathers probably did not evolve for flight, but instead served as insulation, much as fur does for mammals, or perhaps as decorations used in sexual displays. This is an example of the early stages of a trait evolving for one reason, only subsequently to be further elaborated evolutionarily by selection for some other purpose. Flight is an ability certain kind of dinosaurs achieved as they evolved longer arms. We call these dinosaurs birds. Despite their close affinity to Maniraptoran theropods, for example, the possession of feathers and the focula, modern birds exhibit two eponymous evolutionary novelties: hollow bones and physiological mechanisms that permit sustained, powered flight. Archaeopteryx has long been regarded as the most primitive avian lineage, blurring the distinction between avian and non-avian theropods. It shows an intermediate mix of characters between theropods and modern birds. The Pygostylia, for example, Confucius ornis and Changcheng ornis, are characterized by more modern features, but do not exhibit reduction in trunk vertebrae, flexible furcula, strut-like coracoids, alula, Carpometacarpus, or fully folding wings. By the early Cretaceous period, only a few million years after Archaeopteryx lived, a diverse array of birds had evolved, with many of the features of modern birds. Fossils in Mongolia, Spain, and China, discovered within the last few years, reveal a diverse collection of toothed animals, with the hollow bones and breastbones necessary for sustained flight. Other fossils reveal highly specialized, flightless diving animals. These diverse theropods share the skies with pterosaurs for 70 million years until the flying reptiles went extinct at the end of the Cretaceous. Flight muscles consume an enormous amount of oxygen during active flight. The reptilian lung has a limited internal surface area, not nearly enough to absorb all the oxygen needed. Mammalian lungs have a greater surface area, but bird lungs satisfy this challenge with a radical redesign. When a bird inhales, the air goes past the lungs to a series of air sacs located near and within the hollow bones of the back. From there, the air travels to the lungs and then to a set of anterior air sacs before being exhaled. Because air passes all the way through the lungs in a single direction, gas exchange is highly efficient. The revved-up metabolism needed to power active flight also requires very efficient blood circulation, so that the oxygen captured by the lungs can be delivered to the flight muscles quickly. In the heart of most living reptiles, oxygen-rich blood coming from the lungs mixes with oxygen-poor blood returning from the body, because the wall dividing the ventricle into two chambers is not complete. In birds, the wall dividing the ventricle is complete, and the two blood circulations do not mix, so flight muscles receive fully oxygenated blood. Birds, like mammals, are endothermic. The dinosaurs from which birds evolved were endothermic as well. Birds maintain body temperatures significantly higher than those of the most mammals, ranging from 40 degrees to 42 degrees. Feathers provide excellent insulation, helping to conserve body heat. The high temperatures maintained by endothermy permit metabolism in the bird's flight muscles to proceed at a rapid pace, providing the ATP necessary to drive rapid muscle contraction. Birds have the greatest diversity of species of all terrestrial vertebrates. Archaeopteryx exhibited many traits shared with non-avian and avian theropod dinosaurs. A key feature of birds is a lightweight, hollow skeleton. Additional features include auxiliary air sacs and a four-chambered heart. That is all for now. Thanks for watching. See you next time.